Welcome back. In this session, we will be looking into the implementation of artificial bee colony optimization. So, in the previous session, we had looked into the working of artificial bee colony optimization. So, in this session, we will implement it on MATLAB. Before we start implementing ABC, let us quickly have a relook at the ABC pseudocode. Looking at the pseudocode, we will also be planning as to how many function files we will be creating, right. So, as you can see, this is the pseudocode of ABC which we have previously discussed, right. So, the input is the fitness function, the lower bound, the upper bounds, the population size or the number of food sources, T is the number of iterations or the number of cycles that we want to implement, and limit is the parameter which will govern the maximum number of permissible failures, and then we need to generate a random population. So, this is similar to TLBO which we have already discussed. So, we will be using the same concept, and then we will need to evaluate the objective function, right. So, we will have a main script file for ABC to begin with, script ABC, right. So, this is script ABC. In that script ABC we will implement this, right. So, similar to last time, we had kept the objective function out of the script, right. So, whenever we required objective function to be evaluated, we access that objective function file. So, we will have that objective function file, right, and here we will have another file for calculating the fitness, right, because as soon as we calculate the objective function, ABC requires the fitness value, right. So, instead of directly determining fitness in the objective function file, we will use a separate function which will just return the fitness value. So, this way we do not need to disturb this objective function files which we have already created, because I can use them directly with other algorithms, right. So, let us not disturb the objective function files, we will separately write a function to determine the fitness, right, and all of this we will implement in the script file, right. So, we will perform employed B phase, determine the probability of each food source, perform onlooker B phase, memorizing and then checking this condition. Here if we see in these two steps, the employed B phase and the onlooker B phase, we will have to generate a new solution, right, and the procedure to generate the new solution is identical in onlooker B phase and employed B phase. In scout phase it is different. So, there what we need to do is for the member, let us say if the nth member is undergoing the onlooker B phase, right, then we will have to select a partner, right, select a partner and select a decision variable which we need to modify, and then randomly vary it using that equation xj plus phi j xj minus xp, right, and then we need to bound this particular variable, calculate its objective function, calculate its fitness and perform a greedy selection. If the new solution is better, we need to bring it inside the population, else we will be discarding that, and we will keep track of trial counter. So, this is common for both employed B phase and onlooker B phase. So, rather than repeating it twice over as part of employed B phase and onlooker B phase, what we will be doing is we will be coding it in a separate function file and just accessing the function file in this as part of this employed B phase and the onlooker B phase, right. So, that is going to be our strategy to implement this ABC algorithm, right. So, let us now move to MATLAB. So, similar to TLBO, whatever we did for TLBO, we will do the same thing over here. First, I will just walk you through the code, right, and then we will get into the debug mode and see what exactly is happening, right. So, the first two lines will help us to clear the command window and clear the workspace, right, and then we are defining the problem settings. So, right now we are solving the two variable problem, both the variables have 0 as their lower bound and they have 10 as their upper bound, and the problem that we are solving is the sphere function. As we have already discussed, MATLAB has an inbuilt function called as sphere, right. So, just to avoid that conflict, we are calling it as sphere new, and then we need to set the algorithm parameters, right. In this case, we have three algorithm parameters. One is the population size or the number of food source, the other is number of iterations, the third one is the limit, right. So, we set these values. So, here we have directly taken NP, which indicates the number of onlooker bees, the number of employed bees and the number of food sources, right. So, in certain implementation, instead of this NP is equal to 10, they will define S is equal to something and then determine NP is equal to S by 2. So, that also we had discussed when we were discussing the code, right. So, the input can either directly be the number of food sources or it can be the swarm size. If it is swarm size, the number of food sources is determined by swarm size divided by 2. So, now that we have set all the required parameters, right, of the problem as well as of the ABC algorithm, we will start implementing the ABC algorithm as such, right. So, here we need 3 variables, right. So, here we are using f, fit and trial. F is to store the objective function value of the food sources, right. Each food source is going to have its own objective function value. So, that will be stored in f. So, the size of f is np comma 1, number of food sources comma 1 column. So, it is going to be a single column vector. Similarly, fit is to store the fitness value. So, in ABC the objective function is not directly used, but the fitness value is calculated using the objective function value, and that is what is used for both the greedy selection as well as to determine the probability. So, we will be using the variable fit to store the values of fitness of each food source, and then we will have this trial vector, right. So, this trial vector is to keep count of the number of failures, right. So, every time a food source is generating a new solution, but is failing to generate a better solution, we will increase the corresponding counter by 1. The size of trial is going to be again NP by 1. So, each food source is going to have its own trial value. In order to determine the number of decision variables, we determine the length of the lower bound, or you could have determined the length of the upper bound. So, that will give the number of decision variables, right. So, now that we have determined the number of decision variables, we can generate the population, right. So, population again we are using the same procedure, right. So, we are creating a matrix using this repmat. So, it will repeat lower bound NP times, plus we are again creating another matrix in this by this, wherein LB minus UB is the range, right. So, within that range we are creating NP times, and then we are doing an element to element multiplication with a random matrix which contains values 0 to 1, right, and the size of the matrix is NP comma D, because there are D decision variables. The length of UB minus LB will also be D. So, this will help us to generate the initial population. Once we have generated the initial population, now we are ready to evaluate its fitness function as well as objective function value, right. So, as we see over here, prob is the function handle which contains spear new. So, as and when we want to access spear new, instead of directly accessing spear new, we can access prob, right. So, prob we are sending the pth member, this p is the index. So, this loop is going to be executed for NP times. So, each time we are sending one population member or one food source, we evaluate its objective function value. So, once we evaluate its objective function value, we need to determine its fitness, right. So, for that we have this function called as calfit, right. So, let us look at what is calfit doing. So, calfit will receive f and it will check whether it is greater than equal to 0 or otherwise. If it is greater than equal to 0, fitness is determined by 1 by 1 plus f, right. So, you need to be careful with this brackets. So, 1 by in the denominator we have 1 plus f. So, 1 plus f is within the bracket, else the fitness is 1 plus absolute of f. So, absolute of f will give the absolute value, ABS will give us the absolute value. So, if I do ABS of minus 5 in the command window, it will give us the absolute value. So, ABS is an inbuilt function in MATLAB. So, it is a fairly simple function, as you can see. It will receive the objective function value and it will return the fitness function value. So, this is going to happen for all the NP food sources. So, with the help of this particular loop, we have determined the objective function value as well as the fitness function value, right. So, before beginning the iteration, what we will do is we will memorize the best solution, right. So, best solution, again this min function we have seen, min of f will give us the minimum value in f. So, this is objective function, right. So, since we are determining the best solution with respect to the objective function, we need to look at the minimum value, right. So, if you wanted the same thing can be done using the fitness value. So, in that case we would have used max of fit, right. So, here what we are doing is we are using min of f. So, that will return the value, the minimum value in the vector f, as well as it will return its location in that vector f, the location where that minimum value is located, that will be returned as int, right. So, with int we assign the best solution, we just make a copy of the best solution and store it in the variable best solve. So, best solve will have the same dimension as your problem dimension. If we are solving a 5 variable problem, best solve will be a row vector with 1 row and 5 columns, right, whereas best obj will be a scalar for a single objective optimization problem. So, here we are using that variable IND and we are copying that particular member from the population and storing it in the variable best all, right. So, now we are ready to implement the iteration loop of ABC. The first step is to implement the employed B phase. This GenNewSolve will generate a new solution, right. It will perform the greedy search and it will give us the updated population and the trial vector, right. Input to this function is the problem, right, which we are currently solving, because if we generate a new solution we will have to evaluate its objective function. So, we need to give this prob, right, the lower bound and upper bound of the problem, because in GenNewSolve we are going to generate a new solution that may or may not be in the bound. So, to bound we will require LB and UB, right. We need to send the population size, because using the population size we will be randomly selecting a member from the population. So, we need to give this population size. I is the current member which is undergoing the employed B phase. So, we need to provide the value of I, right. P is the population or the food sources. So, from P we will have to extract I, which may get modified, and we will also have to select partner from this P, right. We need to send the value of the fitness for performing the greedy selection strategy. We need to provide the trial vector, because if the newly generated solution is better, then we need to appropriately set the trial of the new solution which is coming into the population to 0. If the newly generated solution is poor, then we will have to increase the counter by 1. So, even that is implemented in this GenNewSolve, right, and then f is the objective function value, we will be passing that also, and d is the dimension of the variable, because remember in ABC we need to randomly select a variable. We are not going to modify all the variables, but we will be modifying only one variable, right. So, to select the random variable which has to be modified, we will need to know the number of decision variables. So, that is what we are passing to this function GenNewSolve, right. And what we are expecting back from the GenNewSolve is the updated trial vector, updated population or the updated food source, the updated fitness and the updated objective function value. So, everything required to generate a new solution is done inside this function, and this is called NP times, because in employed B phase every food source there is no condition to be checked, right. In the employed B phase every solution will get an opportunity to generate a new solution, right. In the analogy of bee colony, it is like every bee is exploiting a particular food source. In our optimization language, what we are saying is that every solution will get an opportunity to modify. We may end up with a better solution or we may end up with a bad solution, right. If it is better, we will take it into the population, else we will discard it, but every member is going to get an opportunity to generate. So, for every member this function is called. Let us have a look at GenNewSolve, right. So, let me open that file GenNewSolve. Whatever the input that we are passing, that is received over here, right. So, first what we are doing in line 3 is we are randomly generating an integer from 1 to dimension of the problem. So, let us say if the dimension of the problem is 10, right. So, if I give 10 comma 1, I will randomly get an integer value from 10 to 1, right. So, that is what this rand d comma 1 is going to help us with. It is going to generate a random integer from 1 to d and it will give us a 1 value, right. So, this 1 indicates that it will give us a scalar value. So, that helps us to select the decision variable which we are going to modify, right. And this p is equal to randi of np comma 1 helps us to determine the partner, right. So, we have NP solutions, the partner is to be selected randomly from one of the food sources or the solutions which we have. So, P is equal to randi of NP comma 1. So, that will help us to select partner. Again this loop is similar to what we implemented in TLBO and in some of the other meta heuristic techniques, that it should not be equal to the solution which is undergoing the employed B phase. So, the solution that is undergoing the employed B phase is n, right. We have received it as n, right. So, n is the solution that is undergoing the employed B phase. So, we just check this condition that if p and n are equal, then we are again generate a random integer. So, this loop is going to get executed till this condition is met, when till p is not equal to n, right. If p is equal to n, it will again generate a random number. This takes care that the partner and the solution which is undergoing the employed B phase is not the same. So, here what we are doing is we are assigning the member which is undergoing the employed B phase to a solution called as X new, right. So, remember we will have to do a greedy selection, right. So, we do not know whether this newly generated solution will be entering the population or not. So, what we are doing is we are just saving that particular food source into another variable X new, right. And then if you remember the equation, so this is the equation, right. So, this phi is a randomly generated number between -1 and 1, not between 0 and 1, but -1 and 1, and this is the equation that we need to implement. We require random number between -1 and 1. So, the strategy which we were employing was LB plus UB minus LB into rand, right. So, the same thing we are doing over here. So, -1 is our LB, not the lower bound of the decision variable, but lower bound for the parameter phi, -1 plus the upper bound which is 1 in this case, minus the lower bound which is -1 into rand. So, this will give us a random value between -1 and 1. With the help of this phi, we generate the new solution. So, the jth variable, why jth variable? Because that is the variable which we have selected to randomly vary, right. So, that is why we are modifying only the jth variable, not the entire solution, right. So, X new of j is p n comma j. Why n comma j? Because we are modifying the jth variable of the nth member, right. The nth member is the one that is undergoing the employed B phase. So, p of n comma j plus phi into the difference between p of n comma j minus p of p comma j. This uppercase p indicates the population and the lower k p indicates the partner, right. So, we are extracting the jth variable of the solution that is undergoing the employed B phase and the jth decision variable of the selected partner, which is denoted by the lowercase letter p, right. So, this will help us to generate new value of the decision variable, and then we employ the same bounding strategy in line 15 and 16, that if the new value violates the upper bound, we bring it back to the upper bound using this min function, right. And if the new variable violates the lower bound, we bring it back to the lower bound using this max function. So, we are not going to discuss this again because we have done this multiple times, right. So, now we have a solution X new for which we can determine the objective function as well as the fitness function, right. So, what we do is to determine the objective function, we pass the newly generated solution to prob, right. That is why we had to send this variable prob in the first place. So, that is a function handle. So, this will get evaluated, right, and that obj new solution to indicate the objective function value of the new solution is passed to calfit. So, calfit will help us with the fitness, right. So, here we have fitness of new solution. So, this will tell us what is the fitness of the new solution, right. Now, we have nth food source which underwent employed B phase, and we also have the fitness as well as the solution of the newly generated solution. So, now we are in a position to do greedy selection, right. So, since we are using the fitness value, fitness has to be maximum. Remember that difference you need to remember in ABC algorithm. So, fitness of new solution should be greater than fitness of the nth solution. So, if this condition satisfied, that means that the newly generated solution is actually better than the solution which was used to generate it. In that case, we need to discard the nth solution and include the new solution, right. So, that is what is done in line 22, that the nth member of the population is entirely replaced with X new, right, and the fitness of the nth member is replaced by the fitness of the new solution. Similarly, we update the objective function value also, right. So, all the three have to be updated, and since this is the solution which is entering the population, we need to set the trial to 0. So, that is what we do over here, that trial of the nth member is set to 0, right. But if this condition fails, that is the newly generated solution is not better, then what we do is we increase the trial counter by 1. Trial counter only of that particular food source, right. So, here if we do trial is equal to trial plus 1, you may not get a syntax error, but that is a conceptual mistake, right. So, we need to increase the trial counter of that particular food source which failed to generate a new solution, right. So, this is what gen new solution will be doing. This completes the employed B phase. So, before going to the onlooker B phase, right, we need to generate probability, right. So, here we are generating probability is equal to 0.9 into fit. So, remember fit is a vector, right. So, 0.9 into fit divided by the maximum fitness plus 0.1. Right. So, this will determine the probability of all the food source. Since MATLAB does that vector operation, even though fit is a vector and max of fit is a scalar, it will divide every element of fit with max of fit and it will multiply with 0.9 and add 0.1, and we will be able to get probability of every food source. Right. Now that we have calculated probability, we can implement the onlooker B phase. So, before implementing onlooker B phase, let us quickly have a look at onlooker B phase. So, this is the onlooker B phase pseudocode which we had. In onlooker B phase, you need to remember that we need to ensure that at least 5 food sources are generated. They may be good or bad, but 5 have to be generated. Initially, since we have not generated anything, we set m is equal to 0, right, and we will be starting with the first food source. So, we assign n is equal to 1, right. So, we will be doing this np times, right, till m becomes equal to np, right. So, if m is less than np, we are supposed to keep repeating this. So, the first step is to generate a random number, right, and then we will have to calculate that random number with probability. If this condition satisfies, we need to do few things, else we need to increase counter of n by 1, and if it happens that the value of n is greater than np, then we need to reset n to 1, that is when this condition fails, right. So, but if this condition does not fail and if this condition is succeeded, then we need to generate a new solution and increase the counter of m by 1, right. So, generating this new solution, this particular procedure is actually implemented in that function gen new solve, right. So, we will just be calling that function again. So, we need to basically implement just 2 or 3 steps, right. We need to generate a random number, compare with this probability, call that function, increase the value of m, irrespective of this condition being true or not, we will have to increase the value of n and then reset n to 1 if it is greater than np. So, we are assigning the value of 0 to m and n to 1, and then we have that while condition, that while m is less than np, right. So, we generate a random number rand, right, and check with whether it is less than the probability value. If it is less than probability value, we generate the new solution, and since we have generated a new solution, irrespective whether we obtain the new solution or not, we need to increase the counter of m by 1, just to indicate that that particular onlooker B has exploited a particular food source, and now we are moving on to the next onlooker B, right. So, that is why we are increasing this m by 1. Otherwise, what we do is we increase the value of n by 1, right. So, here both those steps we have implemented in just one, right. Let us say n is equal to 1, right. So, mod will give us the remainder after dividing by np, right. So, if n is 11 and np is 10, mod of n comma np will give us 1. So, you can look into this mod function, it will return the remainder. So, for the first time when we are executing this loop, n will be equal to 1, right. So, when we do mod of 1 comma np, the answer will be 1, right. So, we are incrementing by 1, right. So, n will be equal to 2. The next time when n is equal to 2, mod of 2 comma 10, if our population size is 10, will again be 2. So, we are doing 2 plus 1 3, this keeps increasing by 1 every time, right. When this n value exceeds np, right. So, let us say when n is equal to 10 and our np is also equal to 10. So, mod of 10 comma 10 is going to return it as 0, right. So, 0 plus 1 1. So, n is reset to a value of 1. So, that is how we have implemented the resetting also in this particular line, right. It takes care of the increment of n as well as the resetting of n. So, this we have done using the mod operator. With line 43 to 49, the onlooker B phase is implemented, right. The next thing is to implement the scout B phase. Before entering the scout phase, what we will do is we will memorize the best solution again. So, this line 51 to 53 memorizes the best solution, right. So, what we do is the objective function values are stored in f, right, and the previous best known is stored in best obj. So, we stack the best obj with f and find the minimum value. So, this min function will return the value as well as the location of the minimum value, right. So, we use that to identify the decision variables corresponding to that solution. So, we combine both the solutions, right, the current population and the solution corresponding to this objective function. Just like we stacked over here, we stack the best solution below the population and then extract the corresponding solution using the variable IND, because IND indicates the location of the best solution, right. So, remember it is necessary to stack this best solve below P, right, because that is how we have done over here for the objective function value, right. So, this will help us to identify the best OBJ and the best solution, right. So, in this case we have chose not to find out the best fitness function value, because fitness function value is not required at the end of the problem. When we are reporting the solution, we ideally report the solution, the decision variables and its corresponding objective function value. So, fitness is something that was required internally for ABC. We are not storing that when we memorize the best solution. So, after that we implement the Scout B phase. So, remember Scout B phase has to be implemented only for one solution, and that too that particular solution whose trial has exceeded the limit set by the user, right. So, in this case we have set the limit to 5, right. So, what we do is we have this trial vector. First we find out what is the maximum value in the trial vector, right. So, if the maximum value happens to be less than limit, then the Scout B phase is not even to be encountered. But if the maximum value in trial is greater than limit, then we need to execute the Scout B phase, right. So, here in this case what we are doing is we are finding out the maximum value of trial. So, it will give us the value as well as it will give us the location, right. So, Scout B phase is to be implemented for that particular solution, right. So, we also need the solution for which the trial is exceeding the limit. Here we incorporate the check that if the value, that is the maximum of the trial value, if it is greater than limit. So, since that solution is going to be completely eliminated and new solution is going to be put into the population, we need to set the trial to 0. So, that is what is done in line 60, that the trial is set to 0, right, and then that particular member P of int. What is int? Int is the location of the population member which has exceeded the limit value. So, we replace that by generating a random solution. So, LB plus UB minus LB dot star. So, we do a elemental multiplication into rand of 1 comma d. So, rand of 1 comma d will generate d random values between 0 and 1, right, and then this right hand side generates a new solution, right. The size of it will be the same as the size of our decision variable. Since this is a new solution, we need to evaluate its objective function value, which is what we are doing in line 62, that we are passing that particular newly generated solution to prob, which is nothing but at sphere new. Once we have determined the objective function value, we calculate its fitness. So, that completes the implementation of ABC algorithm, right. Once the number of iterations have been executed, we still need to identify the best solution. So, it is not necessary that the best solution is best OBJ, and it is not necessary that the best solution is in F, right. It can be either in F or the best OBJ. So, we combine the objective functions. F is the objective function values of the current population and best OBJ is the previously known best objective function value. So, we stack that and find out the minimum value, right. So, that will give us the best OBJ and its location. Then in order to identify the decision variables, we stack the population with the best solution known so far and then use the location obtained in line 67 to extract the best solution. If you have observed carefully, there was an issue over here, right. So, here we are defining the function handle, right. So, the name of the function handle was prob, right. Again we are using the same variable name prob for actually storing the probability value, right. So, this can cause an issue. The rest of the things just remain the same. Over here the code that we are going to actually execute, we have sorted it out, right. So, prob is a variable name which contains the function sphere new. We have renamed this variable from prob to probability, right. So, this will have the probability values, right. So, we will use prob for accessing the function and probability for accessing the probability values for each of them, right. So, the rest of the things remain the same. So, since we changed to probability here, we also change to probability here from prob. So, this completes the implementation of ABC. now that we have seen the code of ABC, now we will get into the debug mode and see its line by line execution, so that we are able to better understand the algorithm, right. So, let me just put a breakpoint over here. So, and if we execute it, right. So, these two you know that it will clear the command window and the workspace, right. We are defining the lower bound. So, LB gets defined in the command window, upper bound gets defined, and prob is a function handle, right. So, and then we define the problem parameters. NP is 10. So, we are working with a population size of 10, right. So, there are 10 food sources, there are 10 employed bees, there are 10 onlooker bees, right. So, number of iterations is 50, limit is 5, right. Now, we will be defining these 3 vectors, right. All of their size would be NP cross 1. As discussed, we are going to use F for storing the values of the objective function, right. So, initially we are defining it as NaN, then we are defining the fitness. So, corresponding to each objective function value, we will have the fitness given by this expression, right. Fitness is equal to 1 by 1 plus f if f is greater than 0, else fitness is equal to 1 plus absolute of f. And then we are defining this trial. So, each solution is associated with a trial vector. We define the trial initially as a vector of zeros and not as a vector of NaN, because these two f and fitness, we are only going to save whatever values we are going to calculate, right. Whereas, for trial what we are going to do is the very first time we encounter a failure, we are going to add 0 plus 1, but if we do NaN plus 1, that will return as NaN, right. So, that is why we are defining it as trial, because we want to keep track of all the failures. And in MATLAB, if you do NaN plus 1, this will be NaN and not 1, right. So, first time when we face a failure, if we have defined it as NaN, then it will return as NaN, it is not going to count this failure, right. So, that is why we are defining it as zeros. So, then we are determining the length of the lower bound. So, D is equal to 2. So, that means our problem dimension is 2, we have 2 decision variable. This step you will be comfortable by now, right. We are generating a population within the lower and upper bounds 0 and 10. We are generating these solutions, right. So, the first solution is 9.3745 comma 7.7311. Now, we have initialized the population. We need to find out the objective function corresponding to each of this solution, right, and then we will also calculate the fitness function, right. Remember, in ABC, objective function and fitness function are 2 different things, right, unlike in the other 4 algorithms where we were talking about unconstrained problem and our fitness function was nothing but our objective function, right. So, here we are running this loop for p is equal to 1 to NP. Right. So, first time we are going to extract this term will give us the first member. This lowercase p is as of now 1, right. So, we are extracting the first row and all the columns. So, that we are giving into this function prob. So, here if we see, it is 9.3745, 7.7311. So, those 2 values are being sent into this function prob, right. So, if I do step in, so here if we see x, it is the same values 9.3745 and 7.7311. Right. So, now it will calculate its objective function value, right. So, the objective function value is 147.6520, and if we go back, so the step is completed now. So, if we do step, right, now it goes into this calfit function, right. So, calfit function is the one in which if we give the objective function value, it will return us the fitness value. Right now, we are going to only send the first value. So, p is now 1. So, f of p is 147.6520. So, that value is being fed into this function calfit, right. So, this f is 147.6520. Since it is greater than 0, fitness will be calculated using this equation. Right. So, fitness in this case is 0.0067. Right. So, if we go back, right. So, this is going to be executed 10 times, right, because our population size is 10. So, every time it is going to populate f of p and fitness of p, right. So, here if we see, f has been populated 147.6520 and fitness is 0.0067. So, this if we keep doing, so the objective function and the fitness function of all the 10 members would get determined, right. So, Now that is complete. So for the 10 members, the objective function value is this and the fitness is this. So here if we see, the least value is 7.7527. Remember, we are working with a minimization problem, right. So 7.7527 is the minimum value, and corresponding to that the fourth value from the bottom, right. This will have the maximum fitness. The seventh solution has the maximum fitness value. So now that we have found the population, we have initialized the population, we have calculated its objective function value, and we have also determined its fitness, right. So the next step is to identify the best solution, right. So that is what we are doing. We are calculating what is the min of f, right. So minimum of the objective function value, right. So that will give us the best objective function value, and it will also give us the index where that particular value is located. So right now index we are expecting it to be 7, because the minimum value in f is located at location 7, right. So if we step, right. So now if you see, this is the best objective function value which we have received, and it is at the 7th position, right. We want to copy the 7th row in the P matrix, right, all the columns, and save it as best all. So that we will have the best objective function value and its corresponding solution. So if we do this step, right, so this is the 7th solution. So if we see P, P if we see, the 7th solution is 2.4755 and 1.2747, right. So that is what is the best solution. So before getting into the iteration loop, we have determined what is the best objective function value that we have so far, and what is the solution corresponding to it. So now we will begin the iteration. So we need to perform ABC for t times, capital T times. As we discussed in ABC, iteration is more commonly known as cycles, right. So if we give this step, right. So now we are into the employed B phase. So in employed B phase, for each food source, these are our food sources. So for each food source, we are going to generate a new solution, right. If the new solution is good, we are going to take it into the population, else we are going to discard the new solution, right. So all that, as we discussed earlier, is going to be done in this gen new solve. Then if we give step, so right now the first food source, so this food source is entering the employed B phase, right, which will be done in this gen new solve. So we are going to send these two values. So we need to send the details about the problem spear new, because we will be generating a new solution. So we will have to calculate its fitness function, the lower bound, the upper bound, because there is no guarantee that the solution which will be generate will be in the bounds. So we will have to do that. We send the population size, because from there we need to randomly locate a variable. We need to randomly select a partner solution. I is the current member which is undergoing this employed B phase. P is the entire set of population. Fitness is the fitness corresponding to this P, right. Trial is the number of failures that each of the solution has encountered so far. So since we are in the first iteration, all the trial would obviously be 0. F is the objective function value corresponding to each member of this population. D is the dimension of the problem, right. So if we step in, right, all these values have been returned. What we had sent as I is actually n over here. So first randomly we need to pick a variable, right, so indicated by j. So this rand I, as you know, if we give d, so d is 2, so between 1 and 2 it will give us a scalar value because we have 1 over here. So right now it has picked the second variable, right. So the new solution which we will generate will definitely have this 9.3745, because we are not going to modify this, we are only going to modify the second variable, right, because this j is 2, and then we need to select a partner. So fifth member, what is going to happen is we are going to use this 7.7311, because the first member is actually undergoing the employed B phase, right, and we will modify this 7.7311 with the fifth solution. So 1, 2, 3, 4, 5. So we will be using this 7.7311 and 6.0418 to generate a new solution, right. So this if you remember TLBO, you would also be able to understand this. So what we are actually doing over here is we are ensuring that the randomly selected member is not the current member, right. So the current member is 1 and the partner we have selected is as of now 5. Had it been 1, it would enter inside this while loop and it may generate some other number. So, this condition is going to be executed till p is not equal to n. So, in this case it will not go into this loop, right. So, that is done, right. So, now what we are doing is we are copying this solution, the first solution as x new, right. So, it is the x new that we will be modifying. So, remember we will have to include the new solution only when if it is better. So, right now we cannot directly do the modification in P, we will generate the new solution and save it as x new. If it is better, then we will include it in P, right. So, in this case we are just assigning the nth member is currently the first member, right, because it is the first member which is undergoing the employed B phase, right. So, if we do this step, right. So, now we need to generate phi, right. So, phi, as you remember, it has to be between -1 and 1. So, the lower bound is -1 plus upper bound is 1, upper bound this minus lower bound into random number. So, this will give us a random number between -1 and 1. So, the random number which it has currently generated is -0.9337. So, that is the phi value, and then we plug into this equation which we have seen, right. So, x new, we need to modify only the jth variable that is unique to ABC. For all the other 4 algorithms we were modifying all the variables, right. Here we will modify only one variable. The value of the jth decision variable of the new solution is the current member which is undergoing the employed B phase, jth variable of that, plus phi into the difference between the current member and the partner that has been selected. So, we were working with 6.0418 and 7.7311, and what we have got is 6.1537, right. So, we changed only the second member, the first member remains as such. So, this solution has now become this solution. So, with this solution we have generated this solution. Now, we will have to see whether this solution is actually good. If it is good, it will enter the population, right. So, then we do the usual bounding. So, again we need to bound the only variable which we have changed, right. So, here we change the second variable. So, we say x new of j is equal to min of x new of j comma ub of j. So, since in this case it is already in the bounds, we do not see any change, we get the same values over here, right. So, now we have a bounded solution. So, now we need to evaluate its objective function. So, objective function is prop, that is why we had to send this variable, right. So, this is a function handle. So, if we do this, it will determine the objective function value, right, and then it is being returned over here. So, similarly, we will calculate the fitness function, right. So, the objective function is 125.74 and the fitness of this new solution is 0.0079. Let us just have a look at F. So, the solution which underwent employed B phase had an objective function value of 147.6520, right, and the one that we have generated is 125. So, it is better, right. So, we could have made this comparison either based on objective function value or on fitness, right, the result would be the same. If we are doing it on fitness, this has to be greater than symbol. If we had worked with objective function, this would have been less than, right. So, here the new solution which we have generated 0.0079 is better than 0.0067, right. So, it is going to enter into this section, right. So, in this section what we are doing is we are assigning the newly generated solution to the nth member of the population, right, and then we are assigning the fitness of the new solution to fit of n. Similarly, we will also update the objective function. Here we updated the population, here we had updated the fitness, here we are updating the objective function value, right. So, now since we have met with the success for this solution, right, the trial has to be reset to 0, right. In this case anyway it was 0, but arbitrarily we would not know whether it is 0 or not. If it had been non-zero, we need to make it as 0 because a new solution has entered into the population, right. So, that is done, right. So, now if we go back, this loop is going to be repeated np times, right. So, for each member we will generate a new solution and we will see whether it is good or bad. If it is good, we will retain it, right. So, if we do step in, right. So, this phenomenon is going to remain the same, right. So, So, in this case just let us see if so fitness new solution is 0.0153, right, and it is the second member. So, 0.0153. So, even in this case the solution which we have generated is actually good. So, fitness new is 0.013 and it is the second member, right. So, n if we see it is 2. So, if we do fit of 2, right, so 0.0125, right, and this is 0.0153. So, even in this case the new solution is actually better than the one used for generating it. So, it will again enter this section, right. So, let us go back to this. So, for the third member again it will happen, right. So, for the third member we have completed the employed B phase, right. So, similarly we can do for all the 10 members, right. Since the procedure is simple, we are not looking into each of that solution, right. So, right now if we look into this trial vector, so for the third solution we did encounter a failure, right. The solution which was initially there would be retained, right, and the trial has been increased by 1. Similarly, for the 9th and 10th solution, the employed B phase did not generate a better solution, right. So, that is why the trial has been increased to 1. So, that completes the employed B phase. Before going into the onlooker B phase, we need to calculate the probability, right. So, fit is a vector over here, right. So, max of fit will be a scalar. So, this probability again would be a vector once we have calculated it. So, this is the probability associated with each of the 10 solutions, right. So, as discussed earlier, we are assigning a value of m to be 0 and n to be 1. We want to generate 10 solutions because our population size is 10. It does not matter whether we are able to generate 10 good solutions or 10 bad solutions, we definitely need to generate 10 solutions in this case, right. So, that is why we have this while loop. So, every time we generate a solution, we will increase the counter of m by 1. So, this n is going to indicate the food source, right. So, for the first time we are going to see whether the onlooker B1 is able to go to the food source 1, right. So, that is this condition over here, right. So, we are going to generate a random number and if it is less than probability of n, right. So, probability of n is currently 1, n is equal to 1, right. So, if that condition is met, we will generate a new solution. So, that actually indicates that particular onlooker B is actually going to the nth food source, right. So, here in this case the random number which we generated was not actually less than probability of n, right. So, that is why it did not execute this, right. So, m if we see it is still 0. Since the first onlooker B did not go to food source 1, we need to increase the food source count by 1, right. So, now we are saying whether the first onlooker B will go to the second food source. So, since we want to move to the second food source, we need to update the value of only n. M is increased only if we have generated a solution. Right now, we did not generate a solution, right. So, m will still remain 0. Currently, n is 1, NP is 10. So, mod of n comma NP is going to be 1, right. So, 1 plus 1 2. So, we have increased the counter of n by 1. Now, the value of n is 2. We again generate a random number, right. So, let us see, even in this case it did not generate a new solution, right. The n value has been increased to 3. So, the first onlooker B did not go to the first food source, the first onlooker B did not go to the second food source. Now, we are looking at the third food source. So, in this case this condition satisfies that the random number which we generated is less than the probability of the nth food source, which is 3 over here, right. So, now in this case we need to generate a new solution, right, and generating the new solution is exactly the same procedure which we employed in employed B phase, right. So, we need to randomly select a decision variable, we need to randomly select a partner, we need to make sure that the partner is not the current member, right. So, current member n is 3, right. So, P is 1. So, this loop will not get executed, right. So, step, right. We are just copying the third member into x new, we are randomly generating phi between minus 1 and 1. So, in this case it is minus 0.1405 and then we are bounding it, bounding the new solution. So, in this case also the bounding will not change the solution because this is within the bounds 0 to 10. So, we get the same solution. now we are evaluating the objective function of the newly generated solution, right. So, the solution which underwent this is 8.998, 7.3409. The solution which it generated is 8.998, 7.1741, right. So, then we calculate its fitness, right. So, fitness again is just given the objective function value. If it is greater than 0, it is nothing but fitness is 1 by 1 plus f, and then we do a greedy selection over here. So, fitness of the new solution is 0.0075, right, and fitness of 3 is 0.0074, because n is currently 3, right. So, n value is currently 3, right. So, this condition is again going to be satisfied. So, we need to include the newly found solution into the population. That is what is being done in line 22, right, and we are assigning the fitness of the new solution into the fit variable, right. Because we updated the population, we also need to update the fitness as well as the objective function value. Since a new solution has entered the population, right, over here a new solution has entered the population. So, the trial of that particular member has to be reset to 0. Now, what has happened is we have completed MS1, right. So, the first solution has been generated. So, similarly we will have to generate 5 solutions, right. So, now in this case the third food sources, we have exhausted the third food source, right. So, the value of n will be increased to by 1. So, n is equal to 4. Since this condition is still not satisfied, m is not less than np, right. So, we generate another random number and see if it is less than probability of food source 4. So, what we are doing is, now we have moved on to the second onlooker B. We are trying to locate a food source for the second B. So, here this condition is satisfied, fourth food source has been selected. We will skip this GenNewSolve because we know what is happening inside that function, right. So, we are increasing m by 1. So, now we have been able to generate 2 solutions. So far we have generated 2 solutions. So, n, if we see, n has been increased by 1. So, n is 5. So, if we continue this, 2 onlooker B's have located a food source. For the third onlooker B, fifth food source has been rejected, right. So, we have increased n by 1. So, n is now 6. Again this condition did not get satisfied. 2 solutions we have generated. So, we are still with the third B, right. So, here if we see the value of n, it has become 7, right. So, similarly if we do it, so in this case for the 7th food source, this condition was true, right. So, again a new solution is generated. So, we can skip that GenNewSolve, right. So, the third B is done, right. So, we have exhausted 7 food sources, but we have completed only 3 B's. So, if we do this step again, over here n is currently 8, right. For the 4th B, the 8th food source did not satisfy this condition, right. So, that is why we are over here. So, n now is 9, right. So, here if we see, we have exhausted all the 10 food sources for now, right. So, n is equal to 10 and m is equal to 3. So, the 4th B is currently going to look for the 10th food source. So, that actually does not happen, right. So, m is equal to 3, but it is not even taking the 10th food source, right. Now, we have exhausted all the food sources. So, n if we see, now if we just had n plus 1 over here, right, then it would go to 11 and we do not have a 11th food source, right. So, that would have been a problem. So, what now we will do is that the 4th B, because 3 B's have been completed, we are stuck with the 4th B as of now, right. So, the 4th B will now explore the 11th food source. So, since there is no 11th food source, we go back to 1, right. So, this mod of 10 comma np will now, this value will be 0, right, and we are adding 1 to it. So, we have gone back to the first food source now, right. So, the 4th B, m is equal to 3 means we 3 B's have been completed, right. So, now with the 4th B, so the 4th B we are exploring the first food source. So, again it does not take in that food source, right. So, the 4th B, because m is equal to 3, the 4th B is, this condition is satisfied for the second food source, right, rand is less than probability of 2. right. So, for the second food source it is able to satisfy this condition. So, we will generate a new solution and this loop will be repeated till this condition is satisfied, right. So, you can execute it and see it. So, right now what we will do is we will just put a breakpoint over here and we will just do this continue, right. So, all the 10 Bs have been completed, that is why it came out of this loop, right. So, now what we have done so far is that all the 10 employed Bs exploited this 10 food sources in the employed B phase. Then what we have done is all the 10 onlooker Bs have exploited one of the food sources, right. So, now we need to go to the scout B phase, right. So, before going to the scout B phase, we will memorize the best solution that we have obtained so far. Remember, we may lose the best solution in the scout B phase, right. Now, let us see the trial, right. So, trial is 1 and 1 and currently our limit which we have set is 5, right. So, scout B phase is definitely not going to happen in this case, but it might happen that one of this trial value is greater than the limit, right. In that case, the scout phase will occur, and since the scout phase occurs, we might lose the best solution. So, to avoid losing out the best solution, what we are going to do is, we have already saved the best solution so far and now we have currently 10 solutions, right. So, what we will do is, out of those 11 solutions, 10 solutions which we now have and one solution which we have saved in this best OBJ, we will combine all the 11 solutions and select the best, right. So, for example, when we do this, it is going to be a vector of 11 rows, right. So, these 10 are the current population, right. So, this F is ending at 30.2610, right, and this is the best objective function value which we have so far. So, we are combining them and finding out the minimum of it. So, the minimum of it is over here 6.7790. So, that will be located at the 7th position. So, this IND will be 7. Once this line is executed, best OBJ will be 6.7790, right. So, because that is the best solution and it is located at the 7th place, right. So, 2, 4, 6 and it is at the 7th location, right. So, similarly, we need to extract the 7th solution, right. So, what we do is, just like we combined the objective function over here, we combine all the solutions. So, P is the current set of 10 solutions which we have, and corresponding to this best OBJ, the solution was best solve. So, we are combining this, right. So, if we just execute this part, right. So, these are the 10 solutions of P, right, and this is what we had saved in this best solve. So, we are just stacking it at the end, right. So, that is what we are calling it as combined solve, and in this combined solve, the 7th row is the best solution, right. So, we will extract that 7th row and we will save it as best solution, right. So, the best solution before these 3 lines were completed was 2.4755, 1.2747, but since we have a good solution of 2.475 and 0.8069, that is getting updated in this best solve, right. So, that completes the memorization procedure, that we are memorizing the best solution that we have obtained so far, and now we are determining the maximum trials that we have encountered so far, right. So, similar to the min function, max function will return us the maximum value in this trial vector, and it will also tell us where it is located. This int variable will tell us where it is located, right. So, if I do this step, so value is 1. So, trial, the maximum value in trial is 1, and the first occurrence is what it is going to tell us, right. It is located at the 4th position, right, and our limit is currently 5, that was user defined parameter. So, we had set it as 5, right. So, this condition is not satisfied, right. So, it is not going to go into the scout B phase, because none of the solutions have exceeded the maximum number of failures which was set by us. So, this condition is going to fail and the section inside that is not going to be executed. So, this completes the first iteration of artificial bee colony optimization. So, this has to be executed t times, right. So, in the first iteration it happened that we did not encounter a scout B phase, but it might occur if the maximum value in the trial vector is greater than the limit which we have set. So, what we will do is we will just put a breakpoint over here, we will remove this breakpoint, right. So I just want to now continue this algorithm, right. So there is no point looking for every iteration, every B, right. The procedure is simple, right, but I want to stop when we actually encounter a scout B phase, right. So that is why I have put this breakpoint at line 60. So now MATLAB is going to execute this program till it comes to this line, right. If it is satisfying this condition, that if val is greater than limit, which indicates that we have encountered a scout B phase, right, then it will pause for our instruction, right. So let me just give this continue, right. So now let us just first say T. So we are encountering the first scout B phase in the fourth iteration. This counter T is the counter for the iteration, right. So T is currently 4, and so let us look at the trial vector, right. So the trial vector has a value 6, right. So the maximum value is 6 and it is located at the 10, 9, 8, 7th position. So this IND would be 7, right. So that is why it has entered the scout B phase, right. So what we need to do in the scout B phase is we need to completely eliminate that solution, right. So the solution corresponding to the 7th is, so IND is 7. So it is going to eliminate this solution 0, 0, right, and it is going to replace it with a randomly generated solution, right. Since we are going to replace this solution, the trial for this, which is currently 6, will have to be reset to 0. So that is what we are doing in line 60, right. So the trial, let us just look at the trial. So we have 6, right. Once this line is executed, line 60, trial of that has become 0 because we are going to plug in a new solution, right. So remember this 0, 0, right. So that solution is going to be randomly replaced. So what we are doing is LB plus UB minus LB dot star rand of 1 comma D. Since we have D variables, in this case 2 variables, we will generate 2 random numbers, multiply it with the range and add to the lower bound, right. So the population, if you see, this 0, 0 is lost. So 10, 9, 8, 7 solution. So 10, 9, 8, 7 solution. So that 0, 0 has been replaced by 9.7260 and 6.0532. Right. So since I have replaced solution, right, I need to replace the objective function value also, right. So now what we are doing is we are sending this, the newly generated solution. So this newly generated solution is given by this to the objective function, right. So if we do step in, right, so x, the newly generated solution, is being sent into the objective function and we are calculating its objective function value, right. So the objective function value turns out to be f of int turns out to be 131.2371. Since we have updated the population, we have updated the objective function value, we are also supposed to update the fitness value, right. Right now this value will be sent, 131.2371 will be sent to this function calfit, right. So if we do step in, so for this solution we are calculating what is the fitness, which is straightforward, right. So now we have eliminated the 7th solution, we have replaced it with a random solution, right, and we have updated the objective function value as well as the fitness value, right. So that completes the scout B phase. So if you have paid attention, our problem is x1 square plus x2 square, right, and the best optimal solution for minimizing that problem is actually 0, 0. So this 0, 0 is the best possible solution, but it got eliminated in the scout B phase, which is what we were emphasizing multiple times, right. So it might happen that this new population we would never get 0, 0 again, it might happen, right, but still we will not lose this because we have saved the solution over here. Best objective is 0, right, and the best solution is 0, 0. So before entering the scout phase, we have saved that solution, right. This is why this external memory part is important, right, that we do not want to lose track of the best solution even if the algorithm does not need it. So now if we continue this, right. So again, so remember we had a scout B phase in the 4th iteration, again in 5th iteration we did not encounter scout B phase, in 6th iteration again we have a Scout B phase. So, in this case the 10th solution has exceeded the maximum number of failures. So, the maximum number of failures is 5, right. So, this has exceeded 5, we will have to replace that solution, right. We will not again go through this Scout B phase because it is fairly simple and we have done it in detail, right. So, let me remove this breakpoint and put it over here, right. So, this is after all the iterations. So, now that all the iterations are completed, okay. So, T is 50, so all the 50 iterations are completed, right. So, F if we see, so there are multiple solutions which have a objective of 0, right. So, what we are doing is whatever the best solution that we have, so this part we are repeating again because we do not know whether the best solution would be in this F or still this best OBJ is the best solution, right. So, what we are doing is we are combining the objective function of the currently available solutions in the population and the best solution which has been discovered so far. We are finding out the minimum of it. It will tell us what is the objective function corresponding to the best solution. It will tell us its location. Similarly, we combine the population, right, the current population and the best solution which we have, we call it as combined solve, and then in that we locate what is the best solution. The best solution is located at the index indicated by this variable IND, right. So, we extract that solution and have it as best solve, right. So, if we give this step, so this is the best solution, right. So, at the end of it, the best solution which we have is given by best solve. The objective function corresponding to this is stored in this best OBJ. So, that completes implementation of ABC, right. So, right now what we have here is as a script file. So, we can convert this into a function file, and again as we demonstrated for teaching learning based optimization, this algorithm will have to be run multiple times for any given problem, and then we need to do a statistical analysis of this, right. As you might have observed, it is fairly simple to implement the ABC algorithm. Remember, ABC does not come as an inbuilt function in MATLAB, right, but we can use this script file and use it in MATLAB. So, with that we complete all the 5 algorithms that we had set out to learn as part of this course. We started with TLBO, then we saw particle swarm optimization, differential evolution, we looked into binary coded GA, real coded GA, and we also looked into artificial bee colony optimization, right. So, we not only learned the theory of all these 5 algorithms, we also solved a problem, right, a small problem, the sphere function, we solved it using all these 5 algorithms, and we also implemented without relying on the inbuilt MATLAB function. We wrote our own code for all these 5 algorithms. Only particle swarm and genetic algorithm is available as inbuilt functions in MATLAB. The reason why we developed our own code instead of relying on MATLAB inbuilt function is that now we totally understand what is going inside the code, right, and on top of that it gives us much more flexibility. So, when we will talk about correction operator while doing constraint handling, you will see that if we have our own code, then it is much easier to modify it as per our needs, right, and you do not need to have an optimization toolbox of MATLAB if you are interested only in using genetic algorithm or particle swarm optimization. So, with that we will conclude this session. Thank you.